Good morning, everyone. Thank you so much for joining us on this March 11th morning for the first in a series of Lodi water management workshops, specifically designed for Lodi wine growers by a great team of UC experts and John Shin, Lodi grower. We're very happy that you're here with us this morning. We've got about 45 people on already. I'm sure several more will join in the next couple of minutes. So I want to make sure that you understand how to use the question box. So right now in the question box, I want you to type in, what is your favorite natural outdoor spot in Northern California that's near water? And this just gets you used to that question box and also gives me some ideas on places to check out on the weekends. So go ahead and in the question box, type in, what is the answer to what your favorite natural outdoor spot near water is? So is it the Delta? Is it the San Francisco Bay? Is it Alamere Falls? That way we'll know that you know how to use the question box. If some of you are here to earn a nitrogen management plan certificate, we do have a way on the back end to see the time that you spend engaged in watching the presentation, so we can monitor the attendance that way. And we will issue those nitrogen management plan certificates within 5 business days. So please don't email us about those certificates until 5 business days have passed so that we can have some time to get those together for you. We were approved for 2.5 hours of nitrogen management plan continuing education units for this workshop. There's a handouts tab in GoToWebinar, and so we do have handouts available for you. Yes, Con, we got the question box, thank you. We do have some handouts for you. We have the agenda for today, also the agenda for the next 2 workshops in this series. So the next workshop will be on Thursday, March 18th, same time, 9 a.m. That agenda is in the handout and also at lodigrowers.com. You do have to register for that workshop separately. We also have a workshop on May 13th. That'll be another Thursday at 9 a.m. and that's on more advanced issues of water management. All of these workshops are designed to help you with practical tips for efficient vineyard water management, and yeah, give you some ideas and give you some good takeaways on how to design an efficient water management plan. And you can register for each workshop separately at lodigrowers.com. You can look at the calendar, or you can go to lodigrowers.com, click on education, click on local opportunities, and events like these are listed in chronological order there. We will have a break at 10 a.m. for 10 minutes. Okay, so now that you've heard me talk for a few minutes about some intro stuff, I think we have almost everybody has joined us and logged in by now and figured out how to get here. So again, welcome so much. We are very happy to have you here this morning for the first in a series of 3 Lodi water management workshops. These were designed by Lodi grower John Shin, who's also a Lodi Rural certified grower. And then we have a great panel of UC experts with us today. And we're all very excited. This workshop was customized to help Lodi growers. And John, I'd like you to take it away and tell us a little bit about why you thought this was important, and the process of putting this together and why you think it's needed. Thank you.
Great, thank you, Stephanie. Like Stephanie said, my name is John Shin, local grower, 6th generation in the Lodi area. So family's been here for a long time, growing mostly wine grapes lately here in the Lodi area. I feel slightly intimidated, even though I know we're not in a room together, but I'm on a panel with all these awesome PhDs, so I feel like a little intimidated, even though we're actually not here together. But I am very grateful. I did some nitrogen management plan continuing education classes online, webinar style, that had been previously recorded, and it was primarily water and irrigation management in North Valley tree nut orchards, and they were fascinating to me. A lot of amazing information about efficient water use, And so I thought, hey, we could use something like this for the Lodi area, because we have different soil types down here. We have a different climate. We have obviously grapes are a different commodity and a different grape with different growing styles. And so I reached out to Stephanie in the Winegrape Commission, and I'm blown away by how fast they got this put together. I mean, it's been like maybe 8 weeks, and we got the UC A&R together, and all these awesome people came with all these great ideas and these resources, and you know, and then Stephanie's like, yeah, we're going to do it in March, and I was like amazed at how quickly this all came together. So what we are looking at here, I thought I've been to a lot of these meetings, grower meetings, grower education, research meetings, and one of the things that we always come away with is a lot of great theoretical information, which is helpful and educational, but I've left a lot of those meetings scratching my head going, great, now what do I do with this on my farm? So one of the things that I worked with Stephanie on this is that how do we take some of this great theoretical information and put it into a very practical way of helping our farming? And I think as a lot of people know right now, and I mean, obviously we can look out there and see, you know, we had this forecast for a ½ inch of rain, you know, maybe more for 2 days. And at least I know on the west side here, we didn't even get a ½ inch of rain. And this year we've barely got 6.5 inches of rain. And water management is unfortunately going to be, if it's not already the hot topic in our industry, will be one of the hottest topics, coming off of a couple of very light rainfall years. We've got Sigma that's coming into effect with management plans being put into practice over the next 10 to 20 years. There's just a lot of things that we need to, as growers, start to take into account to be more efficient with the resources that we do have. And I know a lot of people have moved from flood irrigation and furrow irrigation to drip irrigation, which has helped dramatically, but that's still one of the things we have to learn to manage more effectively is our irrigation management practices. And I think in the long run, how can we maximize both the quality of the grapes that we produce out of this region, and part of that is our irrigation practices, and also the probably limited resources we may have going forward with the amount of water, either surface water or groundwater that we have access to. So, and then, you know, one of the other things, and one of the reasons why I wanted to reach out to the Winegrape Commission is through the Lodi rules practice. One of our big sections is water management, and having an efficient and effective water management plan for that certification process, or to just even improve the practices that we're using out there for our Lodi rules certification. I mean, it is just one of those ideas. I look at Lodi rules as being an opportunity and a foundation for sustainable agriculture, but there's always more that we can do to improve upon what's already there. So, you know, getting better at how we utilize our irrigation and the water resources that we have, I think is just a great way of looking to be more sustainable for our future. So that's kind of it as far as what I've got. I know we're moving into now, starting to get into the meat of our program here. So I would like to introduce Dr. Khan Kurderall, the viticultural specialist from UC Davis, who will be talking about grapevine water relations.
All right, let me share my screen if I can figure out. People can't see my screen from what I hear, right?
We can see it. Just turn it into a slideshow. Yep, we can see this screen. We just need to see the slideshow.
Okay.
If you go to slideshow, then we'll see it.
Yeah. All right. Well, thank you, Stephanie and John, for inviting us to this meeting. And I will start my talk. I was asked to speak about initially the grapevine water relations, just the basics. and then we will move on to more applied stuff. Water is, of course, important for grapevines. First of all, it's a solvent. It has gases, minerals, and other substances dissolved. It's the site for all metabolic reactions. 70 to 95% of the plant mass is water, and it is essential for maintaining the structure, the hydrostatic skeleton of the plant. It is a reactant. It's a substrate for photosynthesis, and it's a currency for the grapevine plant. It's traded to the atmosphere for carbon dioxide to continue the plant's life cycle. And of course, it does have cooling effects for the plant. The vineyard water balance, as you have gone through like classes, I'm sure you've seen this idealized depiction of a grapevine plant growing in a pot, one of which we used to have at the Kearney Research Station in Fresno County. The change in soil water can be described as the precipitation and irrigation sum subtracted, the evaporation and transpiration from the soil and the plant, and the runoff. So the gains and losses will equal to the change in soil water. However, it's not as simple. We do not grow plants in a pot, and there are factors that impact vineyard water use. The evaporative demand, which Daniela will speak about, growth stages of grapevines, which I will talk about later, presence or absence of a cover crop, canopy, trellis type, row and vine spacing, slope and direction of the slope the vineyard faces, the health of the vineyard, soil types, which May will speak about, rooting depth, and soil type all affect the vineyard water balance. There are forces that drive the movement of water from one place to the other, and we describe this as the water potential. It's the measure of the potential energy of water relative to pure water. Usually we measure this in bars in the lab. It's referred to as 1 megapascal, the SI unit. Pure water at room temperature at the sea level has a potential of 0 bars or 0 megapascal. So it's 0. That is pure water. Water movement is driven by differences in the water potential, and it will continue until equilibrium. So just like most things in life, it will move from a higher potential to a lower potential. So it'll move from a higher potential of 0 to a negative. Of course, the high end of the water potential gradient is the soil. The soil water potential that will define the highest potential of water. So during daytime, the soil has the higher water potential, followed by the roots, the stems, and the leaves. The transpiration stream is what establishes the water potential gradient through the plant that drives water flow. And atmosphere has the lowest water potential in the soil plant atmosphere continuum. At nighttime, these are somewhat in equilibrium because the stomata, the invaginated openings under the grapevine leaf are closed. In the absence of transpiration or a transpirational pool, plants are said to equilibrate with the soil in which they're rooted. The low end of the water potential gradient is the air. There's a relationship between relative humidity and water potential. There's a simple formula of describing the potential of water vapor. So I was looking at some CIMMYS data recently, and I plotted this out at 10 degrees Celsius, 20 degrees Celsius, and 30 degrees Celsius. Lodi in July is right around like a 57 to 60% relative humidity. And then the water potential here is, very negative. So there's going to be a, very high demand for irrigation in this region, which we already know. The changes in water potential as soil dries, as you all know, the water potential of saturated soil, we will assume to be, 0 as the leaf starts pulling this water through the soil profile through the roots, you will see this diurnal variation through the time of days. You can see this water potential started very neutral value of 0, which is very high. In about 7 days, you'll go to about like negative 15 bars of water potential, which is very, very negative. There's also the hydraulic distribution of deep water. Okay, and we are able to document this through our sensing, so on and so forth. It was kind of known, but not necessarily proven. Not only from roots to leaves, but water also moves from wet soil to dry soil via the roots through rhizosphere networks. For example, deep water in the soil, that would be defined as soil water below 75 centimeters of the soil down to about 5 feet, will have a higher water potential and lower soil depths, and these will be distributed as the transpirational stream will pull the water through the roots, through the vines. So this is called the transversal hydraulic distribution grapevine. It was shown at UC Davis many years ago, roughly about 15 years ago now. And then now we know the mechanism of how the plants are able to pull water from deeper portions of the soil. Berry dehydration, this usually happens post-veraison. It's a backflow phenomenon. I have 4 insets here of perfectly turgid grapes, somewhat dehydrated grapes. C is when we're starting to see a lot of dehydration, and D is raisin grapes. This is water transport driven by differences in water potential, because berry water flow will require to have less plant water potential than the fruit. So in cases of severe stress, so on and so forth, the water in this tissue gets pulled back into the water stream into the grapevine, because the grapevine berries remain hydraulically connected to the network of the plant later on into the season. Of course, there are components of water potential. You have the gravitational water potential. This is the effect of elevation of water in relationship to one place relative to the other. This will depend on the height of the grapevines. For example, some of the low trained grapevines, such as the vertically shoot positions compared to a single high wire, might have this minimal effect. There's also the matrix potential of the grapevine. This is the effect of interactions with small pores where water molecules are attracted to surfaces, and this is best shown as squeezing a sponge, where water is adhering to the open spaces in the sponge, if you can think of it that way. So soil at full saturation, the gravitational water potential is the excess water in soil pores that drains out, and this is usually not available to our plants. There's also the capillary water. This is water left in soil pores after excess drains and are held in place by surface tension, and this is usually the amount available by plants that can be pulled up into the plant via the transpirational stream. There's also the hygroscopic water. This is held at very high tensions, and this is usually extracted with oven drying, and this is not going to be available to our plants. So if we look at this, in an idealized graph, which will make better sense than me, because I'm not a soil scientist, the surface area per volume of soil particles going from sand, silt loam to clay, you're going to go 2 orders of magnitude to 3 orders of magnitude in difference. So the volume of soil water is then related to the particle size in the soil. So unavailable water as you move along this continuum is going to increase with clays, and available water will reach a saturation point somewhere between loams to silt loams, which is majority of the soils that you will have in the District 11 region. There's also the effect of dissolved salts, which we refer to as the osmotic water potential. We usually see this when we fertigate and when we do not chase it with enough water. When we inject KTS like Agro-K, etc., into the vineyards, and we do not chase it with at least quarter acre inch of water, we will see the effect of dissolved solutes as they rise up to the surface of the soil water potential. So in addition to gravitational matrix, there's also the osmotic potential of water that will be involved in this formula as well. I want to briefly talk about the root pressure in grapevines as we're moving into a bud break in our wine grape growing regions. We already have gone through a portion of bud break in raisin grapes in our Fresno area. The root pressure in grapevines can be defined as essentially priming the pump. As you prime this pump with the available water in a saturated rhizosphere, water will flow into a higher water potential into the lower potential in the root zone or the root tips via this apoplastic route, and it'll follow into the stream, go through the Casparian stream into the xylem cells, which is right behind the cortex of the root tip, which suberizes later on in the season, and that's how the system is primed. This root pressure in grapevines is essentially coming from this somewhat open network in the system, which is going to be modulated by a little bit higher amount of sugars that are present in the xylem that will pull this water into the transpirational stream. So the movement of our water into the roots is, not something very exciting. There's a little bit of difference between rootstocks. Some are going to be more drought tolerant, such as 110R versus 10114. The suberizing endodermis is different between the different family crosses. That's why 110R is a little bit more drought tolerant compared to 10114. This suberizing exodermis difference is what makes all the difference, how they can make these connections later on in the season. So this root pressure in grapevines, it signals activation of roots. It'll rehydrate buds. It'll deliver cytokinins from roots. Sometimes I get questions about if I can apply cytokinins directly to soil. It really does not make any sense. You will refill cavitated vessels that were evacuated during droughts or phloem transport. We have had some recent problems with bud break under drought. Root pressure only will generate after water becomes available again, such as in-season irrigation begins. Fine root rehydration will disconnect the roots from the soil under severe droughts. Plants will usually sense and balance the canopy with root activity. So our recommendation would be to fill soil profile in late winter to assure adequate bud push. So in Fresno Merced corridor, this usually equated to 6 1/4 inches in that area, but we have not done the work in our Lodi area. Other components of water potential will be the pressure of our liquid water. The pressure of our liquid water, which is psi p here, the last item in the formula, is going to be a 0 at atmospheric pressure. It can be a positive or negative. When it's positive, it's coming from root pressure. When it's negative, it's the transpirational pull that's coming from the leaf and atmosphere continuum that's pulling this stream through the xylem of the plant. There's the cohesion, tension mechanism of water transport. This is how the water moves through our grapevines. It's driven by transpiration. So remember, it'll move from a higher water potential to a more negative water potential. The most negative water potential is the atmosphere. So imagine we're starting at 0 in the soil, about a negative 0.25 in the roots. That'll prime the pump. As soon as it gets into the xylem, as the water molecules attach, and then they're under tension from the transpirational pull from the atmosphere, they'll get pulled along this stream, which are these, essentially pipes in the grapevine trunk, and the shoots and the leaves. They'll get pulled out into the atmosphere. These may be disrupted by cavitation. Grapevine is thought to be very susceptible to cavitation. They really are not. There's embolism of propagation, embolism propagation through the pit membranes in the vasculature network of the grapevine. This embolism is mainly a difference potential of negative water flowing in the stream versus what's in the air. And this little embolism here that you're seeing as a little finger jutting into the water stream is what can propagate through the vasculature network under droughty conditions. As I mentioned, grapevines were thought to be very susceptible to drought-induced embolism. As soon as there's an embolism in the xylem network, the water will find a way, and then it'll start flowing. So it's not really something to worry about if people are trying to sell you products such as sap flow sensors, etc., that can sense these, save your money. There's also a drought-induced embolism that can block xylem vessels. So as you're going from as drought takes on hold, starting at negative 18 bars, negative 19 bars, negative 21 bars, negative 27 bars. This is when you start seeing embolism blocking xylem vessels. But this is a extreme condition that we hardly ever will see. As you'll see, the rays here are blocked by embolism. Water is not flowing because there's no water at negative 27 bars. The plants are dying. What happens is that cortex will disintegrate to disconnect the fine roots from the drying soil in these extreme drought cases. However, the plant can remake these connections if you rewater them, depending on the genetic makeup of the rootstocks. In this case, 110R crosses seem to be making these connections much better than 10114 as an example, and they can withstand these droughts a lot easier. We also worry about Turgor pressure. It's the positive hydrostatic pressure in a cell. It's the balance of outward pressure of cell membrane, which is osmotically driven water uptake, and the rigid cell wall pushing it back. This is what makes the berries turgid, not necessarily dehydrate. And at equilibrium between cell water potential, when it's at 0, in this case, osmotic potential, and the pressure of water is, essentially in equilibrium, and it will be, in a perfect balance. When we look at the Turgor loss in our living cells, when the water potential outside is lower than the potential inside, water flows out of the cell, and the Turgor will fall to 0. And this is when we start getting the death of the cells, and stuff wilting. So we use it for the plants use it for cell expansion, plant movements, and structure. The hydrostatic skeleton is maintained by the Turgor pressure of the grapevine as well. So what we use it the most for is stomatal opening and closing throughout the day. It's the influx and efflux potassium in and out of the guard cells induces the rapid change in Turgor, and that's how plants do their photosynthesis and gas exchanges. Here's a generalized response of plant processes to water stress. This is from Professor Shao from 1973. It still holds true. As increasing drought stress takes on hold, we start seeing a lot of changes in the plant, and then throughout the course of this plant water stress, the immediate response is stomatical closure, decreased photosynthetic activity. With decreased photosynthetic activity, what we get are these dehydrated leaves that are starting to fall off around the cluster zone. These seasonal long-term responses are usually, of course, decreased yield, leaf shedding, and decreased bud fruitfulness. And as a response in the grape area, we might get increased secondary metabolites. So I'll sum it up here. It's a long and involved lecture, which we usually deliver in like 2 sessions. I tried to summarize it as short as possible. Water relations are an integral part to vine health and, of course, productivity. Irrigation may allow you to manage most aspects. Factors such as rootstock, variety, soil type, trellising, irrigation system, these all need to be considered. And with that, I will stop my share screen. I did 21 minutes exactly.
You are great, Khan. Thank you so much. So now we're going to turn it over to Dr. May Columber and also Dr. Khalid Bali. Dr. Columber is the UC advisor for Fresno County, and Dr. Bali is the irrigation water management specialist at UC Kearney. So they're going to do a co-presentation for you on soil characterization for efficient water management. Thank you.
May, I think you're muted.
Can you hear me now?
Yes.
Yes. Okay, good. Okay, thank you, Stephanie, and thank you for the invite to talk today. We're going to continue on with, giving you some basic information for grapevine water management and talking specifically about how to characterize your soil for efficient water management. And I'll be giving some of the presentation for the first few slides, and then Khaled will give you some more information for the second half of the talk. So soil is a complex mixture of living organisms, organic matter, soil, mineral materials, water, and air. And the composition of your soil is really dependent on the texture and the relative contents of particles of various sizes of sand, silt, and clay in the soil. And the proportions of those particles influence the ease of which your soil can be worked and the amount of water that it holds. And then it also determines the rate at which water can enter and move through the soil. And as Khan so eloquently explained, soil particles come in different sizes, with sand being the largest in this range of 0.05 millimeters to 2 millimeters, and then silt being quite a bit smaller, and then clay even much smaller than that. And so depending on the composition of these different particles in the soil, that can really have an influence on many aspects, including your water holding capacity, your nutrient availability, etc. So just to show you the scale again, with the sand particles being very large, silt quite a bit smaller, and then clay the smallest of the particle sizes. And because of these different diameters in your soil particle size, that's going to influence how much water the soil can hold. So even though sand has a single particle of sand has a much higher surface area, when you're thinking about this in terms of the volume of soil, clay, which has many, many more individual particles in the soil matrix, is actually going to have a much larger total surface area for water to adhere to in the soil. And so when we apply water through irrigation, water moves much more quickly through a soil that has a higher proportion of sand particles than soil that is dominated by clay particle makeup. And another way of looking at that and thinking about the different proportions could be to look at this USDA soil textural triangle. And so the triangle indicates what percentages of each one of those particles you have along each side of the triangle. So a larger proportion of clay from 0 to 100%, you're going to have that higher water holding capacity. But as water holding capacity goes up, you see a decrease in permeability. With increasing sand, we see increasing permeability, but reductions in water holding capacity. So again, less water holding potential with the sandier soils and higher water holding potential with the clay-based soils. When making an assessment of this yourself, of what your soil texture is, Khaled will go into a little later, how to do this just as simply as doing a texture by feel method, where you're out in the soil, you're looking at different levels from the surface with the changing soil horizons, and trying to get an idea, okay, within the effective rooting depth of my grapevines, how much moisture can the soil hold? And so this graph is an indication of with changing soil type, we have different levels of water content. And so as Khan mentioned, sandier soils will have less overall available water. And then as far as irrigation management goes, what we're concerned about is maintaining our soil moisture somewhere between field capacity and what we call allowable depletion, or 50% depletion. Clay soils, because they have that stronger cohesive forces in the soil and in the soil matrix, they're gonna hold overall more soil moisture, but as the soil begins to dry, it is increasingly difficult for plants' roots to extract that water from the soil. So, but it's very important to understand what your texture is of your soil throughout the rooting depth on your property, so that how much moisture does the soil hold, and then what is the frequency, and what rate should I apply the water at. So this is keeping in mind not just the water holding capacity, but how well does water infiltrate into my soil. Okay, so the understanding permeable and impermeable soil layers is important to get at that irrigation rate and timing, as I just mentioned. So the arrangement of sand, silt, and clay particles, as well as chemical transformations in the soil by translocation, by water movement through the soil structure, and then also the parent material, are going to contribute to the structure and the permeability of your soil. So single grain and granular conditions are where individual particles in the soil are not well aggregated together, or they're loosely aggregated. And we typically find this structure in the upper layers of the soil. As we get more into the deeper layers of soil, the subsurface, this is when we start to see a little bit more structure to the soil. And the way that the structure develops is with time and pressure and the translocation of particulates and materials from the shallower surface down to the subsurface, we get these chemical transformations and then what we call translocations from the upper surface. So that with time and pressure and moisture, we begin to develop this more developed structure in the soil. But when you get that more developed structure, the permeability can decline. And so this is why, and Khaled's going to show you when you're looking at the soil profile, how to characterize it. It's good to know what these characteristics are like so that you know how water moves through the profile when you irrigate. And then finally, those very lower subsurface areas are where we're generally going to see slower infiltration of water. You can't see platy. You can't see platy characteristics in the shallower layers of the soil, and oftentimes this might happen in heavier soils that potentially have the clay and silt fraction under compaction. So that's also something important to look for so that we understand how water drains in response to precipitation and irrigation management. In regards to those horizons, when you use some of the online tools that Khaled is going to go over, you're going to see information that's going to explain your horizon layers in terms of different letter designations. And so just to quickly go over what those are, your O layer is going to represent a very shallow layer, maybe generally about 0 to 2 inches above or from the surface of the soil. And this is going to be this slightly to highly decomposed organic matter. It's usually really rich in color. A lot of times it looks more like litter debris than actual soil, mineral soil. And then this A layer has more of that granular structure that I mentioned, and it's mostly soil mineral fraction, less organic matter, but it has this dark color from that organic matter influence. And so this top 12 inches in the example here is going to be a really important area for nutrients and moisture for your crop. As we get into the B layer, that's where we start to see we can still see granular structure depending on the soil texture, but we'll generally start to see more of this blocky or prismatic structure that's influenced by the accumulation of material that's percolated down from the O and A layer, or by chemical weathering driven by plant roots in the soil or by soil microbes. And then the C layer can be that blocky, platy, or massive structure that I mentioned, and that's typically characterized by cemented sediment. You can have more carbonates down here, higher pH down at these levels. And so at 30 to 48 inches, this is well within the rooting zone of a portion of the roots. And so it's good to, if you're starting from the beginning with planting a vineyard and designing an irrigation system, it's really good to get a good sense of what the profile is on your field. And so I mentioned a little bit about rooting depth. So the average rooting depth for grapevines is about 6 feet, but the top 2 feet make up 90% of the effective rooting depth for your soil and water management. And so just to conclude this beginning introduction, that texture and structure information for your soil layers within the root zone, you need that to estimate your water holding capacity and what your infiltration is like for precise irrigation scheduling. And Khaled, if you're going to continue from this slide, are you there?
Yes, yeah, thank you.
Okay, all right.
All right. Great, thank you so much, May, for giving us an introduction to soil texture and soil structure. And I'll take it from there to see how we can use that information in making irrigation decisions. So, we already know the kind of soil we're dealing with, finding out what kind of texture and structure. Well, we can go to the field and take a sample and send it to the lab, and they can provide us the information back. Or we can get a general idea. There are several websites available on the net that can give you a general idea about the soil texture and a lot of helpful soil information. So one of these web resources is the UC Davis Soil Resources Lab, which is free, available to anybody. All you have to do is just go Google that link and click on the location of your farm. Can I get the next slide? Okay, so for example, this is a farm in the Lodi area. So once I went to that website, I get a map showing the soil texture that I have in my farm. And, this can give you an idea. Okay, so we have two soil types, soil type 101, which is basically sandy loam, and soil type 256, fine sandy loam. So what does it mean? It means that, in general, I would expect to have these two soil types in my farm. Now, how can we take this information and use it for irrigation management? May already mentioned the rooting depth for grapes, 6 feet. Keep in mind, a lot of this information came when we used to have lots of flood irrigation. So with the flood irrigation, typically you're dealing with a deeper soil profile. Now, almost everybody uses drip irrigation. With the drip irrigation, we're most likely limited to the top 2 feet of the soil profile. So we want to pay attention to the top 2 feet of the soil profile, but also we want to know and understand what's going on below the 2 feet when it comes to drainage and salinity and other factors that will affect our irrigation decisions. Can I have the next slide? Okay, so the soil survey web will give you an idea about the soil type, but the best thing is just to go to the field, as you do always, and get at least an auger or a shovel and take a look at the soil profile in your farm. I would also do it not in just one location. I would go to several locations in the field and get an idea about what kind of soil that I have. With a backhoe, I can go up to 5 or 6 feet and take a look at the complete soil profile. So the soil web will give me an idea, but it doesn't mean that what I see on the soil web is what I have in my farm. Can we have the next slide, please? So this is a good example. We went with a backhoe and we dug a soil, soil profile, and you can see here these two soil samples, the one on top and the one on the bottom. They're completely two different textures, even within the same spot. So I want to know and have an idea about, how much of that soil is in my field. Is it just 6 inches of my soil profile, or 12 inches? The bottom soil sample right here, it's a completely different texture. Like the top one, it looks like it's a light textured soil from experience. The bottom one, it looks like a heavier soil texture. So knowing this information will give me an idea about, how I can use this information for making irrigation decisions. Can I have the next slide, May? And I can go take a soil sample, and it's relatively inexpensive to get the texture analysis. You can get the texture analysis. You can get also the EC, electrical conductivity. That will give you an idea whether you have issues with salinity which we will discuss in the future workshops. There are several ways to figure out what kind of texture you have. The most accurate way is to take a sample and send it to the lab. They can come back and tell you, okay, well, you have 20% clay, 40% sand and 40% salt, and this is your soil texture. Another way is to take a sample and take a look at, feel it. The feel method is relatively good. And once you have an experience with it, actually you can make, pretty accurate decision in the field. I would say maybe within 10% of the actual conditions. So if you take a look at this slide with the field method, on the upper left, we're looking at sandier soil, and it's wet soil. As we go to the right, top right, the middle, we have more and more clay, and if we go all the way to the upper right, that's relatively clay soil. So you could see the top three pictures, it's going to wet your hand. It means you have moisture there. Now, even within the soil, the same soil texture, we go down to the bottom three pictures. You could see that, the soil moisture content is less and less. And actually from the field, with the experience, I can correlate this soil moisture with the with looking at my plant or taking stem water potential or other measurements, that will give me an idea. And I can make, good decisions about, well, the soil is dry and it's time to irrigate. Can we have the next slide, please? Okay, so as we mentioned earlier, we want to take a look at the soil profile through the entire depth. And again, with the drip irrigation, keep in mind, we're only, managing most likely most of the uptake is from the top 2 feet of the soil profile. So how can we, from soil, knowing the soil texture, how can we determine, how much moisture our soil can hold? Well, we can use this equation, determine the maximum water depth applied per irrigation. So if I'm irrigating today, I want to make a decision for how long I need to run the system. And we're not going to go into too much detail today, but we will do it typically through the end, at the third workshop. So we already said that we're going to, have information about soil texture and available water holding capacity. We already know the root zone, and in this case, we assume it's 2 feet. If you have different, when you do the backhoe and you look at the soil profile, if it's like 3 feet, you're gonna say, well, okay, my effective root zone is 3 feet, not 2 feet. Management allowable depletion, that's basically depends on the soil type, the texture, and the crop. And then we have to do get an idea about irrigation system efficiency. If you have a drip irrigation system, most likely everything working fine, most likely you're going to have about 90% efficiency. You can easily determine this system efficiency by conducting what we call DU, distribution test, and that will give you an idea. If your distribution uniformity testing gives you an efficiency of about, like, let's say 70 or 75%, it means you have to take measures to improve the efficiency and bring it up to about 90 or 95%. So we can use this simple equation, applied water. Basically, it's the management allowable depletion divided by 100 because we're talking about percentage, and WA, which is the available water holding capacity that we will find from the table in the next slide, and the rooting depth. So in our example, we have 2 different soil types. So let's take a look at this one, sandy loam. And by the way, this table came from the publication that Daniele shared with you here in the chat. So sandy loam, for any given foot, I'm going to have about 1.2 inches of available water. Now, if I, if you remember that that field has two soil types, sandy loam and fine sandy loam. If I'm looking at the block where I have the fine sandy loam, I have more capacity in the soil to hold moisture, so it's at 1.5 inches. So I can use this equation, water applied management allowable depletion divided by 100 times WA, and the rooting depth divided by efficiency. Okay, so this is also the table from the publication that Daniele shared with you. Again, in grapes, it shows the effective root depth is about 6 feet, and this is correct if we have flood irrigation system. Since we're dealing mostly with the drip irrigation, I would say the most of the root uptake is within the top 2 feet, and the management allowable depletion for grapes is 65%. If I'm looking at a different crop, sensitive crop like beans, it would be like 40%. But grapes, we can go with 65%. So I can take this information and plug in the number. If we can go to the next slide. So what water applied management allowable depletion divided by 100 times WA times ZE divided by efficiency. So from the table, we found that management allowable depletion is 65%. We're dealing with a sandy loam with a water holding capacity of about 1.2 inches per foot. And the effective rooting depth is 2 feet, and our irrigation efficiency is 90%. So I can plug the numbers here. And basically, it says the maximum water that can be applied in any given irrigation is no more than 1.6 inches. Well, it means, I want to make sure that I don't apply more than 1.6 inches. If I do apply more than 1.6 inches, the soil is not going to hold that water. And the extra above 1.6 inches is going to go below my effective root zone. Now, we need to get an idea. Well, okay, so 1.6 inches, that's great, but what does it mean? You have to know what kind of application rate that you have. And most likely, you can do from the DU, distribution uniformity testing, you can get an idea about your application rate. Another quick way to look at the application rate is looking at the flow meter, finding out the volume, flow rate per minute or per hour, and looking at how much area you're irrigating in any given set. That will give you an idea about the application rate. Like let's say in this example, if our application rate is 1/10 of an inch per hour, it means that I can take 1.6 inches divided by 0.1, means I cannot irrigate more than 16 hours. So if I irrigate for 16 hours, I'm going to be able to hold that moisture in my top 2 feet of the soil profile. If I do more than that, it means that I'm going to lose that moisture and most likely going to lose energy and nitrogen. May, can we go to the next slide? So basically, this is a very simplistic approach to see how we can use the soil information to make the right irrigation decisions. May talked about soil texture and soil physical properties. We did not talk much about the infiltration rate. Infiltration rate is essential to know, especially if you're designing a new irrigation system. You want to make sure that the new irrigation system is designed correctly, and you need to know what kind of infiltration rate that you have in the field so you don't have standing water, and you can make irrigation decisions. So if, for example, if you have high infiltration rate, you don't want to have long irrigation events. You want to have short and frequent irrigation event. Another thing that you have to consider is soil spatial variability. Even though you can go and look at the map of your field, you may have variability from one location to another, which means like when you're making irrigation decisions, you want to irrigate different blocks differently based on the soil variability. Applying the right amount of water to optimize profit is a key, because you'll end up saving water. And whenever you're saving water, you're saving energy and the nutrients, and reducing greenhouse gas emissions, and reducing leaching of nitrate. We need to consider soil physical properties and consider practices to improve soil health. CDFA, I'm sure all of you are familiar with the Healthy Soil Program. CDFA has money, and there's more money coming up in this next fiscal year for the Healthy Soil Program to do practices where you can apply compost or other measures to improve soil health and get funding from CDFA. Soil texture and rooting depth, we will use this in more detailed example on how we can use it for making the right irrigation decisions, and to make irrigation schedule for ours. And with this, we conclude this session. Thank you.
So thank you so much to Dr. Columber and Dr. Bali for talking to us about soil characterization. Now we're going to switch the program over to Dr. Daniele Zachariah, who's the Ag Water Management Specialist for UC Davis. He's going to talk to us about evapotranspiration and grapevine water use, and he'll go until about 10:20, and then we'll have our 10-minute break. Thanks, Daniele.
Danielle, you're on mute.
Yeah.
All right. I think Stephanie, you had to unmute me. Anyway, I'm going to cover the main concepts and drivers of grapevine water use. Now, this is an important piece of information, especially in years like this one and 2020 that got somehow very dry, and the dry year got somehow overlooked or undetected because there were other emergencies to consider, like the COVID-19 pandemic. But anyway, I think it was a very dry year, 2020, and it looks like it's going to be another dry year. So in my presentation, I'll try to keep it short and simple, review some basics of crop evapotranspiration, or ET, what we call ET, and describe a little bit the methods to measure and determine crop evapotranspiration. And at the end, I will talk a little bit about the different uses of evapotranspiration information at the different scale. Now, ET, so crop water use, is an energy dependent process. And so basically ET is the transfer of water from crop areas to the atmosphere. Sometimes is referred as to a water loss, but it's actually a gain for the plant, because as Characterization mentioned, this is very important for carrying nutrient and CO2 to leaf tissues, and also to regulate the plant temperature. ET is mainly driven by the amount of energy that is intercepted by the plant's canopy, in this case by the vine canopy, and the canopy encounters this energy as a direct radiation from the sun, and also as a radiation from other energy sources like scatter radiation, reflected radiation, as well as the warm air coming from advection, and also wind moving air, masses of air towards the canopy. Here's an example of what we get from direct radiation to the canopy, and indirect radiation, so like reflective radiation. Also, we might have advection, so movement of warm air to our vineyard from other areas, and also we have wind that represent a source of energy. Anyway, the combined effect of this direct and indirect energy sources on the plant's canopy and on the soil surface basically determine the amount of water that evaporates from the soil and transpire through the vegetation. And this is when the soil moisture is not limited. Now, in terms of practical drivers, the topography of our vineyard and also the vine row orientation can significantly affect the amount of energy that the plant receives. And given that light interception is the main driving force of ET when water in the soil is not limited. There's various methods to determine crop evapotranspiration. I'll give an overview here. There are scientific methods, we call it eddy covariance, and those eddy covariance towers normally use a sonic anemometer to measure the wind speed and direction, but also include a gas analyzer to measure the concentration of water vapor and carbon dioxide in the air. This is something that is mostly used for scientific purposes and not for practical purpose to irrigation scheduling. The two instruments give a direct measurement of the fluxes of water vapor and CO2 leaving and returning to the crop surface, and this will give a direct measurement of water evaporated and transpired. We got also for research purposes the lysimeter. Those are large scales. They are basically in the soil. One is a Kearney, the other one is a UC Davis. So again, this is for scientific purposes, and those measure ET by accounting for all the amount of water that gets into the volume of soil that is somehow measured in weight, and the amount of water that evaporates and transpires. So basically, those are called weighing lysimeters and are installed in the ground, and the plants are grown on top of the soil, and those measure all the amount of water coming in and leaving from this known volume of water. There's also some plant-based direct measurement of evapotranspiration. One is, for instance, so you see here in the picture, what is it called, sap flow, and measure this sap flow, measure the amount of sap flowing through a known cross section of the xylem, and there's a relationship between the amount of xylem flowing and the amount of water actually transpired through the plant. But also we got some other instrument. There are, for instance, here in the picture, again, is called infrared gas analyzer. This is a portable handheld instrument that measure the amount of gas exchange between the leaf and the atmosphere. All this direct measurements are mainly for scientific purposes. There are also indirect methods. The first one is called the two-step crop coefficient approach. Basically, we can determine or estimate the amount of crop evapotranspiration by multiply the reference evapotranspiration, which is related to grass, and you can get information from Simmons Station in California by a crop coefficient. And the crop coefficient is normally used to account for all the factors that are somehow regulating or affecting the difference in water use between a reference crop that in California is grass, well-watered grass, and the specific crop of interest of the cash crop. Here is an example of available values of the crop coefficient. I think this was a research conducted by my predecessor, Larry Schwanko and Turgor Pressure in the Lodi and Fresno area. And so you get a sense of the crop coefficient over the course of the growing season for a 50% shaded vineyard at max canopy development. We also can use a soil water balance approach, and the soil water balance approach was briefly described also by May and Khaled. But basically, what we do with the soil water balance approach, we try to account for the amount of precipitation, the amount of irrigation, the amount of deep percolation and upward water flux and runoff and change in soil water storage. And this is basically the principle of a water budget. But there are sources of uncertainties. First of all, we don't know exactly where is the root depth of our specific grape unless we dig trenches and we try to be more precise. And also the other source of uncertainties are the deep percolation and surface runoff. So somehow those are indirect methods. And there's also remote sensing technique there. You probably, as a grower, you get inundated by and overexposed by a lot of this proposal by vendors or service provider. There is a possibility to determine, to estimate, I would say, the crop evapotranspiration through remote sensing, but those are still, I would say, at the research level. And most of the time we saw that the estimate through remote sensing lack of a specific calibration and ground truthing. And so we got a lot of somehow misconception about how to use thermal infrared and multispectral images and DVI and all that stuff in order to determine the crop evapotranspiration. I would say when this remote sensing techniques are somehow claimed to give good answers for irrigation scheduling on a weekly basis, I would say there's a lot of sources of error if you don't do a lot of site-specific calibration. And so I would say maybe solutions are coming with time, but I don't think we are still there yet, especially for crops that somehow benefit from some water deficit like grapes or almonds and other crops, specialty crops in California. But anyway, what happens normally in the reality is that the main source of energy for evapotranspiration is the solar energy. And when the solar energy basically hits the atmosphere, part of this radiation gets scattered and reflected back to the atmosphere. Another part somehow is used for changing the air temperature, and what we call H here as a sensible heat flux. And some other part of this solar radiation gets stored into the soil profile and generates soil temperature change. When the solar energy hits the soil and the soil is wet, somehow this energy is used for vaporized water, and so we have soil evaporation. And when this solar energy finally hits the canopy of our crop, then the plant is in good water status. There's a water vaporization through the plant tissues, and this is what we call transpiration. Now, here is on the top corner a simplified energy balance equation. So we got the net radiation, which is the amount of energy that is available to vaporize water, and that net radiation get partitioned in a ground heat flux with G. Sensible heat flux is the amount of energy that heats the air around the canopy. A latent heat flux, this is the term that we are looking for. So this is the actual evapotranspiration. So we can recombine this equation in a simplified terms, and we can determine the LE, which is our ET, by measuring net radiation, ground heat flux, and sensible heat flux. And this is an example of what we normally do, and I'll show you more detail. So here is basically we determine ET or latent heat heat flux, which is the amount of energy that is being used to evaporate and transpire water, to vaporize water, by measuring the shortwave and long-wave radiation coming in and leaving and being reflected by the crop. And this is what is called net radiation. And also we measure the amount of energy that is conducted into or out of the ground. And we measure the amount of energy that is used to heat the air around the canopy. Here is what we do normally. We measure the net radiation through a net radiometer. This is a micrometeorological sensor. We measure the ground heat flux with two types of instruments, a soil heat flux plate here on the left, and soil heat temperature probe. And then we measure also the sensible heat flux with two types of instrument. One is with the sonic anemometer that you see here on the right, and also with fine wire thermocouple. And this is following basically two methods, two scientific methods for measuring sensible heat flux. One is the eddy covariance, and the other one is the surface renewal. Here's a bunch of pictures of what we normally do for research, and you can see station ET measurement station in the Sierra foothills, and this is, I think, is in the central one is in the Lodi area, and some other measurement station that we deploy basically this year because we have a large grant to reevaluate ET and crop coefficient of wine grapes within what is called the California Crop Coefficient Science Collaborative. This is basically a large grant, a research grant that we got awarded from the U.S. Bureau of Reclamation for measuring ET and determining the crop coefficient of the 10 major water demanding crop in California. Now, this is our last installation last week. We installed this measurement stations in the Fresno area, and we got here in the lower picture also another measurement station in Napa, in the Napa Valley. Now, you can do this measurement fully on the ground, or you can do partially on the ground and somehow estimate some other parameter through satellite remote sensing or airborne remote sensing. And this is, you can do fully ground measurement or fully ET estimate through remote sensing. We truly believe that one cannot do with the other. And so when it comes to remote sensing, we really need to have a lot of ground truthing and a lot of calibration and validation from the ground. So what we call the hybrid method combines the use of ground measurement with remote sensing estimate. So basically what we do normally, either with the airborne platform or satellite, we estimate the net radiation, which is actually not difficult to do with remote sensing. We got here an image of on a vineyard in Chile with the spatially distributed amount of net radiation over the vineyard. And then we measure on the ground the sensible heat flux with the fine wire thermocouple or with the full eddy covariance equipment like 3D sonic anemometer. Here on the lower corner, you see basically the commercial simplification of ET measurement station that was developed at UC Davis. This is a commercial vendor. We're not endorsing anyone here, but just wanted to let you know there are very simplified methods to measure ET in your site-specific condition and your management-specific condition of your vineyard. Now, here's a comparison of what we do for research purposes with respect to what is done with the hybrid approach. In research, we measure most of the parameters. So we measure net radiation, we measure ground heat flux, and we measure sensible heat flux. In the commercial version of the scientific instrument, there's also one measurement of the sensible heat flux with the fine wire thermocouple, because and this is done with a measurement of a high frequency temperature variation above the canopy. The net radiation in case of the Thule station or commercial versions, the ET measurement is estimated with geostationary satellite. So with the fully scientific ET measurement, we are in the order of $15,000 only for the equipment, while with the basically with a commercial version, simplified version, we are at the level of $250 per unit. So there's a clearly an advantage in using this commercial device. Now, it's clear also that another piece of parameter is important when we do this type of research is basically the light interception. Is an example of Mark Battany in the area of Paso Robles, measuring the canopy size and light interception with what he calls the Paso panel. And here is our measurement in the Sierra foothills on a north-facing block and a south-facing block, and we can clearly see a different development of the canopy size over the course of the year. And so a larger canopy basically means more radiation intercepted by the vines, and is supposed to mean, if the water is not limited in the soil, is supposed to mean a higher ET. For larger canopy. Now, there's a bunch of other models available out there for estimating ET via remote sensing. Here's a quick list. I'm not going to go into details because there will be another presentation in a follow-up session. But what I wanted to point out is in most of the remote sensing model, somehow the canopy size or the canopy reflectance is estimated to this vegetation index that is called NDVI, or normalized different vegetation index. Is basically an index of greenness. So the greener is the canopy and the larger is the canopy, the higher is the NDVI. And it combines the near infrared, the reflectance with the reflectance in the red, in the visible, in the red band. And here you got on the top somehow an idea how the different wave spectrum wavelength are used for measuring the NTVI. Is a very old, very old, about 50 years old, and there's a much better now on the scientific development. There's much better vegetation index, and somehow we don't think that NDVI is very well related with the crop coefficient, especially for crops like grapes and pistachio and other crops, where you have some kind of physiological response to the different abiotic and biotic stress. Anyway, here's the deal. With the near infrared, the more green biomass you have, the more reflectance in the near infrared. With the red band, the more green biomass you have, the less reflectance. So by combining this digital number, you get a sense of how big is the canopy size and the greenness of your vineyard. But what happens in the reality is that because vineyards are grown with a different type of trellis, and those are what we call discontinuous or not homogeneous stands, so it's not like a full canopy plant like alfalfa or wheat. So we got some kind of reflectance. So when ET is somehow estimated by remote sensing, you got reflectance in by the soil, by the shaded area, and by the canopy. So this is an example of what you get with 1 meter pixel resolution. You got a combination of the canopy, the shadow, and the soil. And so and this is a major source of uncertainty, especially with parameter like NDVI. Here's an example of a study that was conducted in the San Francisco San Joaquin Delta in California in 2015 to 18, where different remote sensing based models were deployed in order to estimate ET of various crops like alfalfa, almonds, corn, tomato, rice in the San Francisco Bay Delta. And as you can see here in July, where you are supposed to have the full canopy cover, you can see all these different models here. There are 5 different models deployed. All these different models gave very different results among themselves, and you really don't know which one is right or which one is closer to the reality, because there's so many parameters to be set and calibrated in these models that really gets overcomplicated. At the end of the story, you can see the different models here on the x-axis and the different amount of water estimated, and you can see so much different between the different models. So, and this is basically a clear evidence that you need a lot of ground truthing, you need a lot of validation, ground validation and data collection. So alone, I would say the ET estimated through remote sensing might be somehow uncertain unless you have a lot of ET station on the ground that you can basically calibrate all the parameters that are needed to by each and different model. So here quickly, we are conducting an updating of the crop ET measurement and crop coefficient information, because this is a large research project, and this type of information is needed at on-farm level to schedule irrigation for optimal year in the different crops, and also to somehow plan for the amount of water and energy that growers will need versus the available supplies, both water and energy, and also to document water use for water allocation by water district, and also to get an understanding in sigma impacted area of the amount of crop acreage that is sustainable with the local water supply, or whether you can maintain or expand, or you have to retire some of the land. And also it's needed to design and implement eventually depth irrigation strategies with respect to maximum water use. At all farm level, this information is needed for compliance to existing regulation like Sigma AB 589, AB Assembly Bill 1668, and so forth. At the state level, this information is needed to update the state water plan for agricultural water management and use, and also for feeding information into statewide financial incentive like CDFA, SWEEP, and NRCS equip. But also at the end of the story, the state also every year and every 5 years estimate the economic water productivity of water for the different areas of California. As a conclusive remark, grapevine water use is regulated by various factors. So the vine canopy size, the vine vigor, the available soil moisture, and row orientation represent the main factor regulating water demand and water use by grapevine. The topography, slope and aspect also play a significant role because somehow regulate the amount of energy that is intercepted by the canopy. But given the large variability of site-specific vineyard condition in California, even in the Lodi area, because of the different soil, different trellis system, the different canopy management, fruit load that you want to keep, and different irrigation strategy, I think is very much preferable to measure actually ET instead of estimating ET based on empirical models or empirical function that were developed in very different areas of the world or very different areas of California. But anyway, ET is only one piece of the puzzle, because in order to be resource efficient in terms of water and energy, you basically need ET, but need some other type of information in order to optimize the irrigation timing and amounts and balance the vegetative growth with the production function. Commission in Grapevine. I'll stop here, and this is just to remind that we talked about ET, but not that ET that is famous on the screen show for evapotranspiration. So I'll stop here, and I'll be available to entertain questions. Thank you so much.
Thank you very much, Dr. Zachariah. That was very thorough and awesome, and we'll hear from you again in about another 30, 40 minutes. So we need to take our break. We'll come back at 10:35 a.m. I'll put up the handout that Dr. Zachariah has shared with us and type your questions in the question box. We'll start right at 10:35 with Dr. Snyder's presentation on weather characterization. Thank you all. So Richard, I don't know if you can hear me right now, but we can see your screen. So it looks like you might be trying to join us, but you're joined and I can see your screen, so we're good. Awesome. All right. So next up, we have Dr. Richard Snyder. He's a biometeorology specialist emeritus from UC Davis, and he's going to talk to us about weather characterization. And I'll pass it over to you, Richard. Thank you, Dr. Snyder.
Thank you. Yeah, thank you for inviting me to talk today.
And if
I'm
you'll
going to talk
just
about
click on that display settings above your PowerPoint slide.
Oh yeah,
Yep.
hold on a second.
Close, right above the word weather. There's display settings.
I don't see it. I see
We're
you.
right there. So display settings just above the word weather. Yep.
I can't get to display settings because your picture is
You're
there.
close. Just there you go. I see your mouse over display settings. If you click on that, and then that will get it so that we can see the slideshow presentation instead of the presenter view.
Wait a minute, it's not doing it. Hold on. Only thing I can see is you. I can see a picture of you. I don't see, I have two screens. One shows my display and one shows you. And I have no way to change anything. I can't see anything.
But we can see your slides.
Okay, well I can talk.
We just need to be able to hear you.
Oh, you can't hear me? Hold on. There's nothing on here where I can change anything. Hide control panel. Here's, okay, now I'm not muted.
Yep, you're unmuted. But we can't hear you still.
No one can see you. This?
We did practice. There we go. I see you. Now I need to be able to hear you.
You have to find the right buttons. Okay.
We can't hear you. Oh, I'm sorry. I can't hear you because I have you in my headphones. Okay.
Okay.
Now we can hear you.
Okay.
I'm sorry, guys. So now if you just go to display settings. There you go.
Settings.
I'm sorry, everyone. Yeah, right there. Above the word weather.
Rick, a little bit to the right. A little bit.
I can't.
It's okay. Just go ahead. Go ahead. We'll see two slides at once. It doesn't matter.
Okay. No, I can't make anything work. There's no buttons for me to push except, wait a minute, let me see over here.
Promise that we did practice beforehand.
It was working before, just to let you know.
You can move it with a keyboard. You can mute the presentation with a keyboard.
Just the arrow key.
You do what?
Use your arrow key, your right arrow key.
Right arrow key and do what?
To move your slides, maybe?
Let me see. There's no way I can reach it now. There's nothing on, all I see is the internet. I don't see the slides at all. I don't see the PowerPoint. All of my stuff is gone. You want me to log in again?
No. So we can see your slides. So if you can go to the bottom of your computer screen and click on your presentation, we can see it. So you're good. So just start talking. There
okay, I have it now, I think.
Great.
Okay.
There,
all right.
You're good. Good to go. Okay, go ahead. Okay. Without any further ado, Dr. Snyder.
Okay, sorry for that. It's always confusing. I couldn't find any buttons to push. So anyway, I was asked to talk about weather characterization in District 11 from average weather data. And I added with emphasis on ET since this is mostly about evapotranspiration and irrigation scheduling. So I'm going to emphasize things that are important for evapotranspiration. You probably already know this based on what Daniele talked about and other people have talked about. We get ETO from CIMMYS in California. You can also get Spatial CIMMYS. I don't know how many of you know about Spatial CIMMYS. And also we have another, National Weather Service has forecast of ET called FRET, and I'm going to talk about those where you can get that information. Okay. So that first one up there, the ETO comes from CIMMYS. I'm going to talk quite a bit about ETO because they wanted to describe the weather and how it affects evapotranspiration in your area. To get the ET of a crop, the ETC, and that's usually considered to be a well-watered crop. Then you multiply ETO by a crop coefficient to get the evapotranspiration of a well-watered crop. And that's what that second layer there shows. And then the third one down shows ETO times KC times KS. And that's to get the actual ET, which is the evapotranspiration you would have if you had some water stress or salinity stress in addition to the KC. So in the case of wine grapes, you're generally going to have at least mild to moderate water stress is fairly common. Probably aren't going to have a lot of severe water stress, which would reduce the transpiration. There may be some, but probably not a lot. But there would be some stress that would affect the growth of the plant. So they're not going to get as big. And of course, you also prune and other things that will affect it too. I'm going to talk about, I wouldn't expect you to remember this equation. The only reason I put it up is this is the equation that CIMMYS uses to estimate reference evapotranspiration. It's an hourly equation. So every hour they collect weather data and they take that weather data and they use this equation depending on whether it's daytime or nighttime. They'll use the upper one for daytime and use the lower one for nighttime, and they calculate hourly ETO, reference ET. And that's the evapotranspiration approximately of a 12 centimeter tall. So it's about 4 inches tall, cool season grass. And that's what we use for the reference surface all over the world. It's pretty much used. So anyway, the main reason I wanted to show that equation is to talk about, it's really, I mean, the equation is kind of complicated. It was developed in the 1960s and it's been refined since then. This one has actually been modified to do calculation hourly. The original one was made to be instantaneous, so like every second it would calculate what the evapotranspiration is. And this was modified to use daily data. It was adopted by the American Society of Civil Engineers back in 2015. And so it's been around for a while now, and it's used all over the world. Everybody pretty much uses this now. There's a daily equation, an hourly equation. We use an hourly equation in California because it's more accurate if you've got mountains and the ocean and other things where you have a lot of breezes moving around, a lot of wind moving around. Then you have to do hourly equations rather than daily. Daniele talked in the last presentation. He talked about how we do energy balance measurements to estimate ET. The reason why I'm showing this again is just to emphasize that LE is latent heat flux, and that is the evapotranspiration, but it's in energy units. It's not in mass units like we do with water. So we're not getting millimeters or inches of water evaporating. We're getting in watts per meter square. We're getting in energy units, and we convert it over. And that equation at the bottom down in the blue, that shows how you convert over to ET. You have to first put it into the right units, and you divide by 2.45, and you come up with the actual evapotranspiration. And he talked about surface renewal of the thermocouples over in the lower right, talked about the soil measurements in the upper right. The sonic anemometer used to get sensible heat flux. The thermocouples used for sensible heat flux. That stuff in the upper right is used for ground heat flux, and the net radiometer is in the upper left. One of the things I want to emphasize is that the thing that mostly affects evapotranspiration is the net radiation. And so if you get the net radiation right, you're going to be pretty close to what the actual evapotranspiration is. So I took some data from the Lodi number 42 station and then the Lodi West number 166 station, both of which have been discontinued now. And I wanted to show you how important the net radiation is. So if you look at this figure, that what it's showing is on the left, it's showing 1996. And the upper one is the ETO and the lower one is the net radiation. Daniele mentioned about net radiation. It's the balance of the shortwave and longwave radiation. So it's how much energy is really coming from the sun and from the sky that can contribute to evapotranspiration. And that is one of the outputs from CIMMYS, for example. And that's what people try to measure when they fly over with satellites and airplanes, and they try to get net radiation. And we measure with that instrument that I showed you. If you look at the 1996, you can see it. There's kind of an upper layer there. Those are sunny days. So if you don't have any clouds, you should be right up there at the top of that curve most of the time. If you look at the ETO figure up above it, remember ETO is the evapotranspiration of a well-irrigated, about 4-inch tall, cool season grass. So it's a irrigated pasture. And you can see that there's a lot more fluctuations up there. Well, if they didn't have cloudy days, you would take out most of those fluctuations. Those big changes are because there were cloudy days, or else, and also you can get it from smoke from fires as well. But anything that blocks the sunlight is going to reduce the net radiation, and then that will reduce the reference evapotranspiration. Also reduce the evapotranspiration of the grapes. So those are the important things. If you look at 2000, it looks, very similar to it in 1996. If you look at the net radiation, they're very similar. You can see those spikes going down for the net radiation. Those are cloudy days or else smoke from fires. I don't know what happens to be in those particular cases there. Up at the top, you can see the evapotranspiration goes up and down pretty much with the net radiation. There's some small variations there from day to day. You can see during the year in both cases, 1996 and 2000. And those are because of differences in the wind speed, differences in the humidity, differences in the temperature. And all those things can cause minor fluctuations in the reference evapotranspiration and also the evapotranspiration of your crop. One thing I forgot to mention back in that equation that I showed, the hourly equations for ETO, is there's a weighting function in the left side of that equation. There was a weighting function on the right side. Those two functions add up to 1. So what happens is when you have higher temperatures, it weights the radiation to be more important in the equation than the air part. The heat that's coming from the air and the humidity and all those effects are over on the right side. So when you have high temperatures, that part is less important. When you have low temperatures, it's more important. So in the summertime, when you're most concerned about evapotranspiration, it's very heavily weighted towards the net radiation. And so that's why it's really important. If you get the net radiation right with any method you use, you're going to be pretty close. And if you start to account for the sensible heat flux and the ground heat flux, you're going to, put some frosting on the cake, so to speak. So that's what I wanted to emphasize. And you can see this was from Lodi number 42, the original one that was down there. And then this is from Lodi West. These years were all leap year. I just randomly picked out leap years just to show you how these things vary. Back in 96, 2000, there's not very much difference between those two. They're pretty similar in both years. And again, if you know that the net radiation has gone down, if the radiation is reduced for some reason, you'll get a big drop in the ET. It's pretty obvious from this figure. And this is from Lodi West. Again, you can see it, but if you look at that 2004, you see a really huge drop out there in the middle of the season. That's during probably the last half of June and early in July, there was a big drop in the net radiation. Well, that caused a big drop in the reference ET also, which would have caused a big drop in the ET of your crop. So that's when, knowing the evapotranspiration becomes really important. Normally, if you look at that one on the right, that's more of a typical year that you might see. The net radiation, again, if you have clear skies, it's going to be up at the top. If you have cloudy or smoky skies, it's going to drop down. And that's going to affect the ETO. You get minor, fluctuations in the ETO, depending on whether the wind's blowing, what the humidity is, and what the temperature is. Just to give you some more information about the weather. Well, this is another one. Oh, this was to compare Lodi West with Oakville. In 2012, they had both stations were working, and so I was comparing Napa Valley because I've always heard that Napa Valley has a very distinct climate different from everybody else. But when I look at the data, I don't see it. It looks like it's almost the same, actually. The net radiation was very similar in Lodi and in Oakville in 2012. In fact, all the Central Valley's, pretty much the same. You don't see a big difference in the radiation. The differences are more in the wind speed and the humidity and the temperature, because the peak radiation is going to be about the same everywhere. So if you look at the ETO figures on the top, they're pretty similar too. So you can't say there's much difference between evapotranspiration, you know, in your area, in area 11, or in Oakville in Napa Valley. They're pretty much the same. I threw in some temperature data. If you look at this figure, this is showing Lodi West 2012 and Oakville in 2012. And I look at that figure, there's almost no difference in the maximum temperature. A little bit. There's 4 times went over 100 degrees in Lodi West and only twice in Oakville. The minimum temperature is about the same. This is the daily maximum and the daily minimum temperature. The TN is the minimum temperature, which is the red color. And then the green color is the dew point temperature. That's the average dew point over the whole day. They're plotted. And so you can see it's pretty close to the minimum temperature. And I don't see a big difference between Lodi West and Oakville in temperature at all. The wind speed and precipitation, there's a small difference. Mainly it's more windy in Lodi than Lodi West anyway, more windy in the spring. And it kind of slows down and get to mid-summer, and then it's during midsummer from June out until September. There's not much difference between Oakville and Lodi West. And the biggest difference in that is the precipitation. There's a little bit, well, there's a little bit more precipitation in Oakville than there is in Lodi West. So that gives you an idea of the weather differences. It's not that different. Now back to where do you get this information? CIMAS has a lot of information. It was started in 1982. Actually, the state of California took it over in 1986. It took us 3 years to figure out how to do it. It was set up. It has a lot of data that's useful for agriculture. It's called near real-time data because it's not current data and it's not the future. It's what's happened up from yesterday and before. So they have records of data all the way back as long as the station is there. Up until yesterday for every station in California. I also want to point out again, your area doesn't have a CIMA station now. And so I would strongly recommend that you get one. If nothing else, you can use it to check against, if you have your own station or something, you can check against it to make sure it's right. The biggest problem I find with stations that are not run by the state of California is they don't have the right surface to put the station over. It should be over an irrigated grass surface with, you know, about the size of a football field or maybe a little bit bigger. And if you don't have that, then you probably are not going to get the right answer. How much area you have depends on that weighting I was talking about before. The net radiation would be you measure solar radiation, it's the same everywhere. And they use an equation to estimate the net radiation. So that's going to be the same regardless whether you have a CIMA site or you have somebody else's site. But what's different is it might affect the wind speed. You know, so if you put it in a vineyard, you're going to affect the wind speed. You'll also affect the temperature and you'll affect the humidity. So if I was doing like powdery mildew model or something, I would put it in the vineyard. If I'm doing ET, I would put it over a grass field. So that's one thing that you should think about. They just put a new station in, I think, I forget the name of the town, Linden. The Cherry Board put a station out there. So that's the closest one to you right now. I guess there was one in Stockton, last I knew. CIMAS, you can get up at the top. I put the link to get into CIMAS. It's a free service. If you look up the upper right-hand corner, you can register up there and you can log in. Then once you've registered, when you're registered, then you get all the data. You get access to everything. So I'd recommend that you register. The only thing they do is keep track of. They like to know who's doing it, who's using the service. Other than that, they don't keep any information on stuff. They want to know, you know, are you a consultant? Are you a grower? Are you a water manager or whatever? And they want to know who's using it and how often they use it, that type of thing. Other than that, they don't care. So that's the way you get into it using that link on the web. You just put it into your browser. This is an example where I went picked up the data from Davis, which is station number 6. I use the Pima Monteith ETO. That's the one that the Weather Service, well, the one that's been pretty much accepted all over the world, the Pima Monteith ETO. It's clear over the right side when you get in there and you look at the data. They put ETO up at the beginning, but then they put ETO at the beginning, and But that was the original one, because we set up CIMUS before they came up with the Pima-Monteith ETO equation. So they added it in, and it's there available to you, and that's the one I would recommend that you use. So let's see. I just did an example. I took out 7 days of data for Davis. This was back in 2018, and just to give you an idea, I picked out the RS, which is solar radiation, the maximum temperature, minimum temperature, dew point, wind speed, and the Pima-Monteith ETO. And it's really easy to do it. They have a really good setup, really well, easy to get the data. And it's useful. When we set it up, when we first did CIMUS, it was done because almost everybody was doing surface irrigation. So it was really ideal for that, because you don't have all the fluctuations. You can't really deal with those. But now when people are using drip irrigation, micro sprinklers, things like that, then it's better to get more frequent data and more forecast data even. Spatial CIMUS, what they figured out was there's about 150 CIMUS stations in California, but there's a lot of space between the stations. And so they tried to figure out a method that they could estimate ETO in places where they didn't have stations. And that's all spatial CIMUS is. It's based on, they use satellites to estimate the solar radiation, and then they use that information, and then they do some models, and they try to estimate what the ETO is in between stations. So you can find the estimated ETO for any place in California. This is an example. I did this. You can put in your zip code. You can put in, locations you can identify, and then you can sign up for it, and they'll send you messages every week or every day. They can send you a message that tells you what your ETO is in that particular location. And so it's really easy to do. You go onto the regular CIMUS site, and on that site it has spatial CIMUS there, and you can sign up for that. And it's useful if you're in a place where you don't have good access to a CIMUS station. This is an example of the spatial CIMUS report, where I get the ETO and I get the solar radiation average, which is what they get from the satellite. And they use that for estimating the ETO. FRET, I mentioned FRET. FRET is forecast ET, forecast ETO actually. It was started in Sacramento. We went to the Sacramento Weather Service a few years back, and we talked to them, and they decided that they'd like to do forecasting of ETO. So it developed from that. It started out in Sacramento, then it spread to California, and now it's spread the whole country. So anywhere in the United States, you can get ETO now. And you get a forecast for up to 7 days. And in our research, we found this to be really useful, because a lot of times growers need to order their water in advance, and it's nice to know, is it going to be cloudy, is the demand going to go down, maybe I don't need as much water, or maybe I need more water. And so having a forecast, you can plan ahead for how much water you're going to need to order. The link to get to it is https:// and it's digital.weather.gov, and it gets you to this page. This page is showing the whole continental United States, and it's showing the maximum temperatures. And I don't have my mouse isn't working here. I don't think. Oh, it is working. Okay, let me see. Working on one of them. Anyway, if you look up at the top, you can see it says maximum temperature in Fahrenheit. It's the second one. It says natural coolness, and then it says maximum temperature. That's a drop-down menu, and you go in there, and there's like 30 different variables that you can get on this map. And towards the bottom, the last 3 are FRET. One of them is FRET daily, and that's the one I would recommend that you use. This is an example. What I did was I went from this one, and I zoomed into California, and I zoomed into near Lodi. So you can see that there's a little arrow at the bottom of that table that's in there that points to Lodi, and it gives the latitude and the longitude, and it gives you what I did this last night, and I clicked it over on Saturday. So it's given me the forecast from Wednesday for Thursday, Friday, and Saturday. And that would have been 0.3 inches over those 3 days. And on Saturday, it's supposed to be 0.11 inches. So it just gives you, it tells you can go through and do one at a time. You can get the evapotranspiration forecast for each day. Of course, every day you can come back and you can update it if you want to. And so they decided to add this FRET service to their their digital forecasts. So that's why it's on this map in this pattern. It's not that difficult to do. If you're a water agency, it would be a really great thing to go in there and get that and put it, you know, for your area, to put it on your local website and read them off, and people can go get it there. That would make it even easier. But it's a really interesting thing. They use the Penman-Monteith equation, but a daily equation. So it's not quite as accurate as the hourly, but it's still pretty good. And it's probably as good as anything that we have. So just to summarize, CIMMYS, that's the link to get into CIMMYS. Spatial CIMMYS, there's an app that you can get from C-Stars. I'm not sure that it's still available. It was available. The guy who developed Spatial CIMMYS resigned and went to work at the library at UC Davis. So, and I think he still runs it. He still has that available. So if you want to get an app for your phone, you can get it. I have one on my phone. And then FRET, that's the link to get into FRET. I mentioned about KCs. I'm going to say just a little bit about KC values. It's not weather, but it's still something that's important. It's ETC divided by ETO. If you have actual ET, then it would be ETA divided by ETO. This is ETC, remember, is for a well-watered crop. Sometimes we don't differentiate. I think eventually it's going to become important. But this is some data that I collected with some colleagues down in your area. Actually, one of them was up south of Rancho Seco, so we called it Seco because we could see it from the field, so we thought that's an easy way to remember it. So it was up by Rancho Seco, and then we also did some measurements down by Thornton. We did them at the same time. What we were trying to do is to find out, is the ET different? Does the soil affect the ET? And so in Rancho Seco, the two fields were about probably 200 yards apart, not very far apart. They were irrigated the same, exactly the same by the grower. One of the soils had 85% rock fraction. So 85% of the volume of the soil was filled with rocks. And the other one had zero rock fraction. And so we were looking to see if there would be a big difference in ET. It was drip irrigated. It was irrigated frequently with drip irrigation. And there was a little bit of a difference. The 85% rock fraction is the red-yellow color in this in that slide for the Secos up at the top. And you can see it was a little bit lower than for the one that didn't have the rock fraction. So there was a minor difference in the crop coefficient. They ran, you know, somewhere up around 0.9, which is pretty high, pretty much higher than what we've been saying for the last 20 years. And we see that all the time. The Thornton was down in an area that had a unlined irrigation ditch ran by one of the part of the field, and so we put one station there, and we put another one that was far away from the irrigation ditch, and the one that's blue was where they had the irrigation ditch nearby, and so you can see it was a little bit higher ET than the one that didn't have the irrigation ditch nearby, so the KC values are a little bit higher. Generally, they started, if you go back out to the beginning of May, it's down around about 0.5 or so, and it gets up to around 0.85, 0.9. Sometimes it'll get up to or close to 1. So that gives you an idea what the crop coefficients are. We've also done on slopes. We find on slopes it's completely different. It makes a difference if you have east-west rows and north-south rows. Usually east-west rows have a little bit higher ET than north-south, but it depends on the wind direction. If the wind blows down the rows, it won't increase it very much. But if it blows across the rows, you get more turbulence and you get more ET. And so it makes a difference if you have east-west or north-south rows. Okay, I want to just make a couple of comments about climate change, because I know that's of interest too. I did a study a few years ago. There were we took 18 CIMMYS stations. And what I did was I put in a possible scenario for what might happen with climate change by the end of the century. And that was assuming that it increased by 3 degrees Celsius, 2 degrees for the maximum and 4 degrees for the minimum temperature. And we increased the dew point temperature by 4 degrees. And we changed the canopy resistance. And that's because when you put more CO2 in the air, the plants close their stomata partially. That reduces the transpiration. And so we took those and I calculated what it was currently at that time, and then what it would be with this scenario. And then using that, we looked at, well, what's the change from the current ETO? And basically, it's not going to change very much. So what this is showing, this is the annual total. So we're talking about the extreme would be 30 millimeters per year, and for the increase, and the decrease, the extreme was about 50 or 60 millimeters per year. So it's 50 millimeters, about 2 inches in the whole year. So the basically what it says is it's probably not going to change. And this line, I plotted it against wind speed, because what I found was that when the wind speed increased, it actually decreased the evapotranspiration, the increase that you would get. So again, this is taking that scenario. I calculated the ET. We took the original data and we compared the two over the whole year, and that's what happened. So if you had high wind speeds higher than about, it's a little bit less than 2 meters per second, so it's about 4.5 miles per hour. There's not going to be hardly any change. And so I don't think ET is going to be a big problem as far as climate change. Evaporation, yes, evaporation will still occur, because if you raise the temperature, you'll have more evaporation. So lakes and ponds and rivers will evaporate more, the ocean will evaporate more, but transpiration will not increase necessarily. So this is just to kind of top it off, is you look at the models that they have for climate change, and they're all over the place for precipitation. This is for Northern California. This came from Scripps Institute down in San Diego. And the models don't agree on how the precipitation might change, but the air temperature models all agree pretty much. And so the air temperature is predicted to go up, by 2 or 3 degrees Celsius, which is a lot. Okay, so when the last ice age, it was 5 degrees Celsius lower than it is today. So, it could be a big thing. What'll happen is if you increase the temperature, it'll have higher evaporation, and also the snow level will go up. And so we won't have as much snow in the mountains, and that's what the Department of Water Resources is really worried about with climate change, is if the snow level goes up, they don't have that reservoir of snow for the water during the summer. So anyway, that is the end of it, and thank you.
Thank you so much, Dr. Snyder. That was really great. And next, we're going to move on to Dr. Zachariah again, and he is going to tie all of this together for us so that we can figure out how to design an efficient micro-irrigation system for vineyards.
That's a no.
All right. I'll try to keep everything short, so I will leave time for a few questions. I'm going to cover a little bit of how we put the normally information together in terms of soil, weather, and plants, and how we can design a resource-efficient micro-irrigation system for vineyards. And normally, when I say resource efficient, is not only water, but it's also energy, because with micro-irrigation, we end up using energy to pressurize water. And lately I got a sense of what a normal grower will pay for water in the Central Valley of California. For let's say a pistachio orchard will be around $250 and about $700 for energy. So the relevant part of the cost for irrigation is not water normally, but is actually energy. So we'll cover a little bit of some design consideration for micro-irrigation system. We'll talk about vineyard water and energy requirements, and we'll I prepare some practical calculation examples, and I'll probably not go into detail, but the calculation examples are part of the presentation. The most adequate irrigation method for grapevine, we have to start from the root system. Basically, the root system of mature grapevine consists of a woody root structure, and they're increasingly smaller absorbing roots that branch in all directions. So, and those roots mine the soil vertically and horizontally, but also those roots to thrive in soil with a good balance, with a good balance between water and air and oxygen. So those have to be unsaturated soil, and the grapes doesn't benefit from soil compaction or waterlogging and long wet and dry cycle. This basically means that low volume micro irrigation is probably is the best solution for a grapevine, because this allow very good control and careful management of both the timing and amount of water and nutrient application, especially in the case we do also fertigation through the irrigation system. As been observed in the past, the surface and sprinkler irrigation have been associated with increasing level of fungal disease on to the vegetation, to canopy, and to the fruit bunches. At the design stage, the aspect where we should focus the attention, I'm covering this aspects not because you have to do the design yourself, and maybe it's good that you know how the design normally is done, and what are the main important aspects that you have to ask to your designer. So first of all, a preliminary site evaluation is very important, where you evaluate what type of water supply you have, the soil type, as the other presenter indicated, and also what kind of variability of soil texture you have in your future vineyard, what type of slope and aspects, and also the vine spacing and row orientation are all important parameter to consider. What trellis system, and also what kind of projected canopy size you will have a full development of the vines. Now, this preliminary site evaluation is also important to investigate a little bit in detail the soil aspects, because the first couple of steps in design is to define the maximum water application rate in inches per hour, and the maximum irrigation depth in inches per each irrigation. And this has to be done based on the soil properties. And so the soil properties, they are more important, as Khaled was mentioning, are infiltration rate and water holding capacity. As a rule of thumb, normally in advanced design, we wanted to apply the peak daily ET, actually the peak daily water requirement in a maximum time of 16 to 20 hours set time, and this is to allow some down time for troubleshooting and repair. Now, what we do normally, we size the different system components from downstream to upstream. We decide the application rate and the maximum irrigation depth, and then we calculate the flow and friction losses along the drip system and along the pipe system, and then we size the various parts with in order to have sufficient capacity for routine and maximum system load. Now, when I talk about maximum system load, there's water and capacity that the system should have for facing heat spell and extreme warm weather during the peak demand time. And also, it's very important to, as a designer, to ensure some operation flexibility to your system. And what I mean by operation flexibility is that during its lifetime, the irrigation system might be operated under different conditions. For instance, when the vines are small, you need a limited number of drippers, and then as the vines grew and grow and become larger, then you increase the number of drippers, you increase the flow, and so the friction losses also increases, so you increase the pressure head. And also we can have blocks at different elevation and different distance from the water supply or from the pump, and that means that the different block might be operated at different pressure head from the pump. And so also sometimes we have blocks with different emitters and different application rates due to significant soil differences. And sometimes we also have in some vineyard composite systems. So those composite systems have drip and micro sprinkler, so and fan jet, for instance, or they have single and dual line, or they can operate with alternating the side that is irrigating, or you can have solid irrigation. So both the dual line operating at the same time. So that means basically you can have different flow rate, different frequency, and different pressure. Another problem that is happening in California, especially in the Central Valley, that the groundwater level either fluctuate over the course of the season or is lowering down over the years. And so we can also have sometimes pump components that are wearing. And so that means that the pump has to work at a higher load. And so that operation flexibility is very important as design, the design stage. So as a first rule of thumb, the application rate that you want to consider for your new vineyard has to be lower the soil intake rate. And here is a graph of the intake rate over the course of an irrigation, let's say from 0 to 6 hours. At the beginning, if the soil is dry, there's a lot of infiltration, but then as the pore space are filled with water, basically the infiltration rate lowers down to a basic infiltration rate. So the basic infiltration rate is our design parameter, because traditionally drip and micro-irrigation systems are operated for long hours. And so we want to make sure that we consider the basic infiltration rate when we decide the amount of water to apply in terms of inches per hour. So we wanted to avoid basically over waterlogging. And here is a table with the different application rate for the different type of system. And in case of drip irrigation, you can see is variable between 0.01 and 0.03 normally on average in terms of inches per hour. So for instance, in this type of soil that I'm considering this specific example, the basic infiltration rate is 0.02. So micro sprinkler might not be suitable because the application rate is higher than the basic infiltration rate. So I'm going to have, after a few hours, I'm going to have a problem over waterlogging. Here is a table just for give you some values of the maximum application rate of your irrigation system for different type of soil and for different slope. And of course, if the slope increase, you want to slow down the application rate in order to give some opportunity time to the water to infiltrate. And so those are also tables that we normally use when we design irrigation system that have to be somehow resource efficient and also benefit from the energy rates. And I'll explain to you in a minute. Also, as a second rule of thumb, the maximum amount of applied water per irrigation has to be lower than water holding capacity. And here's a table that I think Khaled and May also already show. So we want to make sure that the amount of water that we apply for as a maximum apply water per irrigation is compatible with the maximum water holding capacity of our soil. And here's a table that gives also some average value that are normally used when we design the irrigation system. There's also an important component is to assess the spatial variability of the soil features. Now we have instruments like Very Soil Survey or other technology like electromagnetic induction, and those survey can detect a significant difference in the soil texture, as you see in this color picture here. This is a real case at Davis in an area where we design a subsurface drip irrigation system for vegetable crop, and so we had to pick and choose values that are critical in order to have efficiency in water application. So normally this technology is available to you at probably at the lower cost. Also, a couple of years ago was was at $40 to $60 per acre. Now it's probably even lower. There's also a quick method to understand and appraise the hydraulic feature of your soil, and this is normally done when we design subsurface drip irrigation, because we can somehow simulate after 1 or 2 or 3 and 4 and 5 hours what is the wet area in terms of vertical movement of water and also horizontal subbing of water, and this is pretty important for irrigation design. Here is a ET-based calculation of maximum amount of water depth per irrigation. I'm not going to spend a lot of time here because I saw that Khaled has already covered, but here is also an example how to calculate this maximum amount of water per irrigation. This is a design parameter. Normally, one thing that is worth talking about is that normally micro-irrigation system used to be typically designed for the lower investment cost. So the pipe system is sized in order to have a lower investment cost. But remember that you're also using the system for 20 to 25 years, and you're pressurizing water, so you're using a lot of energy. So the real cost over the year it's the energy cost and not the investment cost. So normally I suggest, when I do design, I suggest to design not for the lower cost, but increase a little bit the capacity of the system to apply water compatibly with the soil infiltration rate, the soil water holding capacity, in order to reduce the friction losses and to minimize the energy cost. I'm not going to cover this in too much detail, but you have here in the presentation, we can also define the soil, the maximum depth of irrigation maximum depth of water per irrigation based on the soil type, and here are the parameter that Khaled discussed about. So our depth of gross depth of water to apply per irrigation is determined based on the soil characteristic and MAD, so management allowable depletion, and effective root depth, and percent wetted area. And I can explain this a little bit better in a follow-up meeting if you want. So once we decide the amount of water to apply per each irrigation, how we calculate this water depth into, how do we convert this water depth in volume per plant? And this is a simple formula and also a table that is used normally. The amount of water in terms of gallons per day per plant comes by multiplying the water depth in inches per day by the crop spacing, and then we multiply by a conversion coefficient, which is 0.62. And here is also a table that will allow to convert this inches of water into gallon per plant. And this is a calculation example for a mature vineyard on Cabernet Sauvignon on 5 by 6 feet spacing, where the vertical should positioning trellis and single drip line, root depth 5 feet, and effective root depth is about calculated as 60-70% of this maximum root depth, and the type of soil. And here the calculation will show that all consider our maximum amount of water to be applied per irrigation comes to 0.8 inches. And when we want to convert this 0.8 inches into gallon per plant, we apply this easy equation, and it comes to 15 gallons per plant per irrigation. So this is a new useful conversion, and it can be used for design purposes. Now, typical flow rate and pressure, this is another important design parameter. Normally for drip and micro sprinkler, we have a wide range of flow rate between 0.5 to 30 gallon per hour at the emitter level, and the operating pressure of the system varies between 20 and 35 psi. Those are important parameters. in reality, the micro-irrigation emitters only require 7 to 12 psi, and those are drippers and fan jet. But also, what increase the pressure requirement is normally the filtering and the conveyance of water from the pump to the emitter. And filters are the critical component because they normally require 15 to 25 psi of pressure and a little bit more if they are a filter provided with a back flushing capacity. The most relevant system components in a system, I always put a flow meter and a pressure pressure meter in different important point of the system. And you might want to put a flow meter downstream of the pump and downstream of the filtering station, but also equip the system with enough point where you're measuring the pressure in order to spot problems and be able to troubleshoot problems in a very timely way. These are also important components that normally we put in the micro-irrigation system. Those are pressure regulator or riser pressure regulator that we normally put, and those help stabilizing the pressure because as you can see, the flow rate at the level of the meter is proportional to the pressure at the inlet of the emitter. Now we have two different type of emitters. The non-pressure compensating here you can see smaller variation in pressure generate large variation in flow at the level of the emitter, and then you can have also pressure compensating emitters where large variation in pressure generate very little variation in flow. So normally I'm very careful even in flat areas, and I always consider pressure compensating emitter when I exceed a certain run, the drip tape, and but also provide in a main critical point at some riser pressure regulator in order to stabilize the pressure and balance the flow into the system. In terms of water requirement of Grapevine, in California, according to our experience, the mature grapevine needs anywhere from 16 to 28 inches of irrigation water per season to grow and produce in an economically viable way. And this really depends on your location and seasonal rainfall that you get, also the type of training system, the trellis, the canopy size, the row orientation, the slope and aspect, and how windy is the area. And grapevine can uptake and use water from different sources. So one source is the moisture stored in the soil profile from winter rain, but also we can have some in-season effective rainfall. We can also irrigate in order to complement what the soil moisture depletion into the soil, but also in some area along the coast, there's some significant contribution of water to ET by fog and dew. Another point that is important is the energy requirement for micro-irrigation. In general, it takes about 1.37 water horsepower per hour to lift an acre-feet of water per each foot of lift. And this comes from basically the Nebraska pumping plant performance criteria, which is basically considered the standard that for the entire US. Now, the different fuel source have different pump output. So if you see electricity here, natural gas at the different British units, and diesel and propane, those are the different fuel sources you might use at the pump level. And all this fuel source, each unit of this fuel source has a different ability as an output at the pump level. So if you divide this 1.37 by the specific pump output of different electricity source, then you get the energy units that are needed for each acre for lifting each acre-feet of water per foot of lift. Now, these numbers are very helpful for you to understand and to plan ahead and to understand the cost of energy to pressurize water into your micro-irrigation system.
So
Here is an
Daniele,
example.
we've
Yes.
got to stop because we only have 1 minute left and we've got some questions. So
Okay,
I'm sorry,
I'll stop here.
we'll have to keep this
Yes.
for the next workshop, but this is
All
all
right, I'll
awesome
stop here.
practical info. So John Shin is going to ask you a question. Thanks, John.
All right.
Great. Hey, thank you guys so much. This has been just really, really amazing information here. We did have 2 questions. I would like to encourage anybody, if you did have questions and maybe you didn't get a chance to ask them or you're not 100% sure how to use that function, please email Stephanie any questions you may have, and we'll try to put those together, get them out to all the panelists, and see if we can maybe get those addressed for our next session on the 18th. So we did have 2 questions. One of them was, what are some ways that we can improve soil structure to improve soil moisture holding capacity? Some practical things such as cover crops, maybe manure, I don't know, anything to build those up. And I think the important part is how long before we might see the change in that structure so we don't throw the towel in too early.
Would you like me to answer that? This
Yeah,
is May.
that'd be great. Sorry.
Okay, sure. Okay, so things that you can do to improve soil structure. That's a really good question. And you know, one of the tricks with that is that you can make changes to soil structure over time, but you can't change the texture of the soil that you have. So whatever you have to start with, you know, in terms of some of those components we were talking about with water holding capacity, and then some of the structural characteristics associated with the texture are difficult to change, but not impossible. One of the most effective means of doing this is by reducing your tillage. Cover crops are also very good at, you know, I mean, they provide root structure in the soil. They're another source of organic matter that feed soil microbes. They increase, you know, the porosity of the soil and the ability of water to infiltrate. So those are the first 2 things that come to my mind. And then in terms of how long you need to invest, you know, in that, I mean, I would say that, you know, I would say within a year, you may notice differences if you were to adopt a, you know, some no-till, reduced-till approach, cover crops. But, you know, in terms of what that might mean for the health of your vines or something like that, you know, that may be a longer term investment. You know, if you're, it depends on what, you know, what property you're hoping to improve. But in terms of, you know, maybe something to do with infiltration, depending on your soil texture, you might see improvements in a short period of time. But yeah, I would say it's definitely worth sticking with. It may take a few years to get those results.
Okay, great. Thank you very much. And the other question along the lines of crop ET, so Dr. Zachariah, was how do we differentiate out the grape ET versus other factors such as permanent cover crop and influences that permanent cover cropping may have on that ET?
Well, we actually, with the instrument that we have, normally we get a sense of the total amount of water evapotranspired, but by the area, by the cropping system. And so basically there's not really many ways of, there's not really a way to differentiate. So normally cover crops are terminated around April, and so what we get is a sense of soil evaporation and crop transpiration. But in case the cover crop is maintained, then we have to make some additional measurement at the level of the canopy, and so that gets into a little bit more complicated measurements. And so, Rick, Snyder, do you have any additional consideration to this? The way we could probably measure the, and differentiate stuff. Probably Rick signed off. Anyway, I think there's no many ways of doing it unless we apply more. Are you there?
People have been working on this for decades, and there's no easy solution to separate, transpiration, whether you have a cover crop or not. Typically, you add 0.2 to 0.3 to your crop coefficient when you have the cover crop. That's what they've done historically for a long time. I haven't really seen any great improvements over that. So there's no easy way to do it.
Okay, well, that sounds good. Again, I know I've got a bunch of different questions from the notes I've taken, so I'm going to forward those to Stephanie as well. And if anybody else, again, has any other questions that you would like addressed, please forward them on to Stephanie, and we'll see what we can do about that. But thanks again to everybody that has participated. Thanks for everybody that checked in to do this. A lot of great stuff. Be sure to stick with it. We got a lot of great theoretical stuff this seminar, and we're going to start putting it together into some more practical uses for your actual property after this. So thank you.
We hope to see everyone next Thursday, 9 a.m. Remember that you have to register for that online separately. Bye, everyone.
Bye.
Thank you
so
to
much.
all of our great speakers today and our wonderful moderator, John.
Hey, thank you, Stephanie.
Okay.